Good morning. This is Professor Grenfell making another video for Math 12 Statistics at RCC. And here we are delving on into Chapter 3, Section 2 with a little bit more detail. I'll go into a few more examples. And here in 3-2, we're talking about measures of variation. So we have primarily the range, then after that the variance and the standard deviation. I'll just kind of denote these in the same color here because they are intricately related to one another. So just say it like that. Okay. All right. So let's just review. In 3-1, we talked about a measure of center. One particular measure of center, the mean. Okay. And here, if we're using this notation, notice that this is the population mean. Oops. Forgive me, my iPad has a little chip right in the screen, right there. Garbles my letters. Anyhow, the population mean, so for that we use the Greek letter mu. Okay, remember it's not mu like a cow, it's mu. All right, so, and what does this mean? This is, the instructions are add up all of the what? All of the x values, and then you divide by the total number in that population. And so in example 3-15, that's the first thing that we're going to just kind of review and practice. Okay, and so here in example 3-15, it's telling us what? We're comparing a couple of brands of paint. And so this testing lab is testing 2 experimental brands of outdoor paint to see how long each will last before fading. The testing lab made 6 gallons of each paint to test. And then since different chemical agents are added to each group and only 6 cans are involved, these 2 groups constitute 2 small populations, right? Okay, so that kind of makes sense. There's only 6 gallons of brand A in the whole world. And so therefore, this is population A, and then similarly for B, it's experimental as well. There's only this many, and that's the whole population for B. So here the instructions are to find the mean of each group. So these would be the population means. Now, whenever I'm going to use a formula, or whenever I know I'm thinking about a concept where there is a formula involved, it's very important for me, I can't stress this enough, but I'll try, to copy down this formula. Not copy it down, recite it, produce it from memory, right? So anytime you use it, write it down first. So here I'm going to say, and try to do it from memory. So don't look at it. So I'm going to just scroll up there so we can't cheat. And I'm going to say, well, let's see, to get the mean of population A, I'm going to take all of the, the X stands for the data, right? And the subscript of A kind of is an identifier saying it belongs to the A population. So this is all the A data. And then we're going to divide by the total number in population A. So there, all of the subscripts just indicate kind of an identity, right? So here, which population mean are we talking about? Well, are we talking about population A or population B? Well, the subscript is what clarifies that for us. And then here, to just kind of remember that we're not, using the A stuff when we're talking about B, we're going to put B subscripts on all of these. So here, these ones are the X subscript A's. Those are the data for population A. And here, similarly, these are what we are calling X subscript B. the first thing that we're going to have to do is find the sum. So the sum of the x values for this column, well, these would be the a values. Here we're going to add this up, and so I'm seeing 210. Okay. The next thing is what is the number? How many items are there in the first population? Well, count them up. There's 6 values there. And so for this first one, we're seeing the sum of all of the a values is 210. The total number that we have in the data set for that first population is 6. So we'll do this division, and we'll get exactly 35. And now the next thing that we have to do is basically more of the same, except now using the second set of data. So right here I have the sum of the x subscript b, and that just means the data from population B. And so we'll sum this up, and see, we get the same value, 210, as we did for brand A. So that's just pure coincidence. The number that we have, also by coincidence, they just happened to make 6 gallons of brand B and test them out. So that is in subscript B, that is equal to 6 as well. All right, so this here, we get the same exact numerical quantities in the top and in the bottom for our calculation for mu subscript B. So the mean for, what was this? I believe the number of months these paints last outdoors before fading, the mean for that population for brand A, the average was 35 months, and same for population B. So here are 2 data sets that have, well, drastically different data. I mean, they have some overlapping values, but the data points themselves are different, and yet they both have the same average value. And so what we did there in 3-15, that was just pure review. So that was measuring the center of the data sets for each of those 2 various brands of paint, experimental brands of paint, I should say. In 3-16, it instructs us to find the ranges for the paints in example 3-15. And here, remember what I always say? I always say you need to write down the formula. And the nice thing about a lot of these formulas is you can actually translate them into words. Remember, any formula or any equation is essentially just a set of instructions in terms of doing these kind of complicated, well, you know, ranging from simple to complicated set of calculations or operations on these numerical values. So if you can translate them into words like this makes a lot more sense than just writing down something like R equals H minus L, because that's just algebra, and this is actually describing what it's for, or how to use it. So for brand A, the range for brand A is going to be the high value from data set A, or population A, minus the lowest value. And so I can kind of glance back up and see this one was 60, right? The high value was 60 and the low value was 10. And so what we get there is just 50 for the range. Okay, so the range is our first kind of most primitive measurement of how varied the data is. So basically, just kind of is a measurement of how spread out the data is. And so if you just take the highest value minus the lowest value, that is one obvious way of getting how spread out the data is. And here we'll just do the same thing for this one. The high from set B minus the low from population B. That was what? The high value was 45 and the low value was 20 for set B, 20, oh, sorry, 25. Okay, so the range ends up being 20. Okay, so here what we're seeing is these data are distributed differently. They're centered around the same point. Their mean value for both of these populations is the exact same. But notice the range for population A is a lot greater than that of population B. And just that one simple metric or some simple measurement for variation, also known as the range, highest value minus lowest value. Let's move on. And here we'll look at 3-18. And we talked about this in the lecture on Monday, the idea of standard deviation and variance. And so here we're going to be using the kind of complicated formula for computing the population variance. That's what we're doing in this example, 3-18. It says find the variance and the standard deviation for the data set for brand A paint in example 3-15. So they listed the data for us, and the first thing that I did is I copied all of those X values down. Remember, these were the X subscript A's, but since we're just talking about one single population, let's not mix it up. Let's not even talk about the B's, so there's no need to say these are all the A values. Let's just take that right off. These are the values from our population, period. Now, I'm writing them all down. We're going to keep track of those, and we're going to be calculating the variance. So that's sigma squared is the symbology for that. And the first thing we always have to do is what? Write down the formula. So here we're squaring some business. There's the X values minus the average, all divided by n there. And then I'm just going to stop there. I'm not going to write down the formula for sigma itself because I'm going to find sigma squared first, and then I'm just going to take the square root of sigma squared. So this statement's just kind of silly, but that's the instructions for what I'm going to do. Now, here's procedurally speaking how we do it. In the previous example in 3-15, we went ahead and calculated the mean, but if we didn't have an example 3-15 that we had done ahead of time, and we just had to compute the variance or the standard deviation, we would have to do that. So we would first have to find the sum of the X values, and that was 210. We had capital N, I just write it right here, capital N was equal to 6. So the first thing we would find was mu was 210 over 6, and that was 35. Okay. All right. Now, sometimes you might want to create a whole separate column right here for saying what mu is, and then the next column would be X minus mu. But since we can remember mu is 35 here, we're going to just say what is X minus 35 for each one of these. So mu is always going to be 35. We're just going to be taking each X value and subtracting 35 from it. And so there are those differences. Each X value subtracted away from it, the average value. And notice these values like 10 and 20 that are below average, when we take their difference, those are negative numbers. Similarly, for ones that are above average, those differences are positive. And so if we did something silly and we just added all of this column up, all of the negatives and all of the positives are going to balance each other out. So don't do that. Don't add up that column. We're just using that column as a helper so we don't have to do two steps at once. In this next column, we're going to be squaring these values from the previous column. And then that is what we're going to be summing up. So, I'll write that in a different spot. But first, I'm going to copy down or produce these values. I don't have to copy them down. What do I do to fill in this blank right here? I just look at whatever this value is, and I square it. So 25 squared is 625. And similarly, negative 25 is also positive 625 when we square it. So any negative number or any positive number, whenever you square any real number, it's either negative times negative or positive times positive, and we get an end result of a positive value. And so here it's important that we're summing up all of these positive values. We don't want to sum up this column here and get 0. That would be bad, right? That would be looking at the wrong quantity. That's why that would be bad. And so that total is 1,750. That right there, what did we add up? We added up all of the x values minus the average value, and then that quantity squared. All right. So now, in order to compute sigma squared, we've already done all of the hard work, right? So we found this quantity in the numerator and came up with that, wrote it down, or at least stored it in our calculator's memory as our first step, right? So we're not even using this formula yet. We're just determining what we're going to put in the numerator. That turned out to be what? 1750. And then here, since this is the population variance and the population standard deviation, we're going to use n itself. Okay, so n was 6 in this formula. Okay, and so we go ahead and plug that into our calculator. Just hit 1750 divide by 6, and that comes out as 291.6 repeating. And the rounding rule is we're going to round to one extra decimal point. So these went out to the ones place, so we're going to round to the nearest tenth. Now, what do we do to find the standard deviation, sigma? Well, we just look at whatever we got for our previous result. We got to find sigma squared, essentially, and then just take the square root of it. If they don't ask us for sigma squared, we'll just do that first anyway, and then take the square root. So we're looking at the square root of approximately 291.7, and I get, taking the square root of that, I get 17.07. If I had taken the square root of the actual value that was left over in my calculator, that, without losing those residuals, would have gotten something slightly different. But either way, those both round to 17.1 when we round to the nearest tenth. Okay, and let's continue. Let's do example 3-19. We're still talking about this situation where they're comparing these two experimental types of paint. We made up two small prototype batches of each one, and each one consisting of a total population of 6 gallons total of this paint. And they're asking now, what is the standard deviation and the variance for brand B? And so I've gone ahead and copied down the data for the X values, the information, the data points for that population B. There these are. And then remember, the first thing I'd better do is rewrite the formula. So sigma squared is equal to the sum of the X minus the mu, whole thing squared, all divided by the total number in that whole population. Okay, so remember, that means procedurally speaking, we got to go ahead and find mu. First things first, And so we'll think about doing that in just a second. But then after that, we have to go ahead and subtract that away from each data value. So let's actually fill that in purple. I got over here, right? And then we're going to take that whole business that we got in that column and square it. So that's what we'll do there. And I left a little space at the bottom to sum each one of these columns. Well, not each one, because remember, we're not going to be summing up these values in the middle, because the sum would just be 0. So no need to talk about that. Don't do it. Okay. And here we'll go. We'll go ahead and sum these columns up. This is 210, right? Mu is equal to the sum of the values divided by the total number of the values. Remember, write down the formula. Okay, that was 210 divided by 6. Yeah, we remember this was 35. Also, the means were the same in both of these populations. Okay, so we're going to take the difference. For each of these x values, we're going to subtract 35 every single time. This first one's going to be 0. 45 minus 35 gives 10. Negative 5 here. 0 again. We got a positive 5, and we got what? A negative 10. And notice we got the exact same values, just positive and negative, symmetric, repeated all the way through. So if we sum those up, that would be 0. Don't sum them up. That's the moral of that story. Square them. That's easy. I'll do all the easy ones. How about that? Okay. Those ones. You can do the hard ones. Oh no, these ones are easy too. Just kidding. All right. So adding these up, you get what? 250. Now remember, here we're going to let's clean this up. We're going to be looking at this equation right here. So we already have this component. We're going to just simply substitute in 250 when it comes to rewriting this equation. We're just replacing this whole part with what we obtained from this procedure. And then here we have n equals 6. So there's that. Okay, so we obtained 250 divided by 6. I had to pause to plug that in my calculator. We get out 41.7. And then for the standard deviation, remember this is variance, and this one is standard deviation. That's how I spell that. Standard deviation, you can spell that. I like that. Anyways, less letters. It's just harder to pronounce. So what do? We just take the square root of whatever we got there. So that, I'm not going to bother writing down. I plugged in the square root of 41.7. I just did that and rounded it to 1 decimal point, and we got 2.6. So notice, compare these. The variance of this one for brand B, the variance and the standard deviation both are considerably less than in the previous example. So here we had 41.7 versus this one we had 291.7. And then here the standard deviation was 2.6. The standard deviation here was 17.1. And let's see. Oh, sorry. Didn't have anything else. So we'll call it a video here. Bye for now.